In this lecture, we study L2 space. So topics of this lecture are following. So the main result we prove here is L2 comma this pair is a non-linear space. And to prove this, we prove two inequalities, namely Cauchy-Schwarz inequality in L2 and Minkowski's inequality in L2. Okay, so let us recall what is L2. L2 equal to the set of all sequences x equal to sequence xn at n belongs to set of all naturals such that summation xn square over n equal to 1 to infinity, that is n belongs to set of naturals. This is finite, this sum is finite. Okay, this is L2. And what is this function? This is function from L2 to set of all reals. Okay, defined by following. This is equal to summation xn square over n equal to 1 to infinity whole power half for x equal to sequence xn in L2. Okay, so now we basically want to prove that this is a norm in L2. So our main theorem is following. Here is the main theorem. L2 comma this, here we have sub 2. This is a non-linear space. Okay. So what to prove? To prove that L2 is closed under addition. L2 is closed under addition. That is for x comma y in L2, we have to show that x plus y belongs to L2. And second, this is a norm. This is a norm in L2. And to prove this is a norm in L2, we have to prove that this is greater than or equal to 0 with equality. If and only if x equal to 0. And second, alpha times x, this is equal to absolute value of alpha times x. And triangle inequality, x plus y, this is less or equal to this plus this. For x comma y belongs to L2 and alpha belongs to R. So this is what we need to prove. And to prove that L2 is closed under addition and this properties, basically in particular triangle inequality, we need to prove two inequalities, namely Cauchy-Schwarz inequality and Minkowski's inequality. So let us first prove Cauchy-Schwarz inequality. So, theorem. This is Cauchy-Schwarz inequality in L2. Right? Let's see. Quasi-Schwarz inequality. So it says that for x equal to sequence xn and y equal to sequence yn in L2, we have xn times yn summation over, so here we have absolute value summation over n equal to 1 to infinity. So this is less or equal to 2 times y. So this is called Cauchy-Schwarz inequality in L2. Now let us prove it. So for every finite n, so already we have proved Cauchy-Schwarz inequality in Rn. So by Cauchy-Schwarz inequality in Rn, by Cauchy-Schwarz inequality in Rn. So in Rn we have xi times yi absolute value and summation over I equal to 1 to n. This is less or equal to xi square summation over I equal to 1 to n whole power 1 over 2 times summation yi square summation over I equal to 1 to n whole power half. Okay, so this is by Cauchy-Schwarz inequality in Rn, and this quantity in the right hand side, this is less or equal to times y norm 2. Okay, therefore what we have, so this implies summation absolute value of xi times yi summation over I equal to 1 to n. This is less or equal to x sub 2 times y sub 2. Okay, and this is true for all n. This is true for all n belongs to set of all naturals. Now if you tend n to infinity in the left hand side, then you have, this implies limit n tends to infinity summation I equal to 1 to n absolute value of xi yi. This is less or equal to norm of x sub 2 y sub 2, and this implies summation n equal to 1 to infinity xi xn yn. This is less or equal to and this is what we wanted to prove. Okay, so this is nothing but Cauchy-Schwarz inequality in Rn. So that work is complete. So next we prove Minkowski's inequality, so which is an application of this Cauchy-Schwarz inequality. So let me write applying Cauchy-Schwarz inequality. We prove the following. Following is so-called Minkowski's inequality. in Rn. Theorem. Minkowski's inequality. So it says that if x comma y in L2, so where x is sequence xn and y is sequence yn, then we have x plus y in L2. Moreover, so basically Minkowski's inequality proves that L2 is closed under addition, and moreover x plus y is norm less or equal to x3 plus y. So let us prove this inequality. So for x equal to sequence xn and yn, y equal to yn, we have summation xi plus yi square summation over I equal to 1 to n. So this is equal to summation xi square plus 2xi yi plus yi square, okay, over I equal to 1 to n, and this is equal to, so let us break the summation. So this is equal to I summation I equal to 1 to n xi square plus 2 times summation xi times yi over I equal to 1 to n plus summation yi square over I equal to 1 to n. Okay, and this is less or equal to, so this quantity, the first summand, this is less or equal to, write another color. So this quantity is less or equal to x2 square, and this quantity, this is less or equal to norm of y2 square. And now this quantity, this is less or equal to, so we have 2, and remaining quantity is less or equal to this. Okay, so what we have is, so finally, so what we have, this quantity is less or equal to this, and this is equal to norm 2 plus y2 square. So now let me write again, xi square plus, sorry, xi plus yi square yi whole square summation over I equal to 1 to n. This is less or equal to, this is less or equal to plus y second square. This is true for all n belongs to set of all naturals, and this is finite, okay, because x and y, these are in L2. Therefore what we have, so tending n to infinity, so left hand side, this is x plus y. So let me write one more line. So this implies summation xn plus yn whole square summation over I n equal to 1 to infinity. This is lesser equal to this is this is lesser equal to x is 2 plus y 2 whole square, and this is finite. This implies x plus y belongs to L2 by definition of L2, and this implies if you take square root on both sides, so we have this whole power half, and now this is equal to norm of x plus y second lesser equal to. So already you have proved L2 is closed under addition, and this is the second addition. Okay. So this completes the proof. Now we prove the main theorem. That is our goal of this lecture. So now we prove this theorem. So now here proof of main theorem. So first we have to show that L2 is closed under addition, and that is already proved. So first we have to prove that this is closed under addition, that is for x comma y. In L2 we have to prove that x plus y in L2. Okay, so in the Minkowski's inequality, in the Minkowski's inequality, we have already shown that for x comma y in L2, this is in L2. This is finite, and therefore this is finite, and therefore x plus y in L2. Okay, now B part. So in B part we show that this is norm. Is norm. So now for non-negativity, x equal to, let's say, sequence xn in belongs to set of all naturals. Then so xn, for every n, xn is real, so xn squared, this is greater than or equal to 0, and therefore this is summation over n equal to 1 to infinity. This is also greater than or equal to 0, and therefore whole power half, this is also greater than or equal to 0. Note that a square root, this is equal to no absolute value of a. Okay, so this is by definition. So we are using this. So this is always greater than or equal to 0, and this is equal to, so this is greater than or equal to 0. Now equality holds. Now this is equal to 0 if and only if summation xi square I equal to 1 to infinity, this is equal to 0. Okay, and sum of non-negative reals, this is equal to 0, This is if and only if xi equal to 0 for all I. 1, 2, and so on. For all I equal to 1, 2, and so on. That is for all I belongs to set of naturals. Xi equal to 0. That is x equal to 0. That is if and only if x equal to 0. Thus non-negativity. The first condition is proved. Now second one. So this is second one, alpha times x. So x alpha belongs to set of real and x belongs to L2. Then alpha times x now 2. This is equal to alpha x n whole square summation over n equal to 1 to infinity whole power half. And this is equal to alpha square power half times summation x n square over n equal to 1 to infinity whole power half. And this is equal to absolute value of alpha times this. And again, triangle inequality we have proved in Minkowski's inequality. Triangle inequality x plus y. Second now, this are equal to this. We have already proved in Minkowski's inequality. So here is stop this lecture.